Hello, welcome to piScanner. I am Professor Sung-Ho Jo, a developer of piScanner. In this video, I'd like to explain what piScanner is, how piScanner test is performed, and how the piScanner data are analyzed. In brief, piScanner is a non-destructive seismic technique which evaluates the modulus and thickness of concrete pavement and possibly an asphalt pavement. piScanner combines two different seismic techniques, SASW test and body wave resonance test. So piScanner tests perform two different tests in sequence. First of all, what you wanted to do in performing the test using piScanner software is to set up parameters for field test. Let's go to the main menu configuration by clicking on the top of it. Let me bring out. Okay, here are two different tabs. The first one is surface wave test. The second is body wave test. So by clicking the name of the title of the tab, you can switch back and forth. Okay, so in case of surface wave test, everything is set up using the default values. You don't have to change anything. And we would like to go over some of the menus. First of all, averages. And then we are going to make 10 tests consecutively. And then the software is utilizing average values out of 10 measurements. So it says 10. So if you like to have just the 5 averages, and then you just change it back to 5. And also, please take a look at source measured. And then in this measurement, we are not using instrumentation hammer, and we are just using steel ball hammers. So we don't need the source measured. And then in case of body weight measurements, and also, and here we would like to use just one number of averages. Or sometimes you may want to use 3 averages. It depends on you, or it depends on the data quality. And most of the cases, I believe just one is enough. And also we can have a source measurement options here. And then also in the case of body weight measurements, and we don't use typically source, instrumentation source. So no is a default menu. Right, after you check all these parameters, and then the last one you have to do is click setup hardware. And then clicking on the setup hardware and set up the communication between the computer and National Instrument device. And then it is ready for running the test, and then also ready for downloading the data onto the computer. And for now, I just close it because I do have data collected already. So let me open it and read the data quickly. Okay, Q is my data. And so let's take a look at the measured data. First of all, surface wave data. And the uppermost one is a source signal. We didn't measure the source, so it is showing just 1 volt initially, and then the others is 0. And the second one is showing the time history is collected by 2 microphones. And the first one is blue, the second one is green. And the blue is coming from the first microphone, which is close to the source. And green one is farther one from second microphone. And the bottommost is phase spectrum determined from these 2 time histories. And then if you go to the body weight measurements, and then the upper one is showing, let's say, the time histories of the first microphones. And the middle window is showing power spectrum of the first time histories. And then actually this is supposed easily the body wave resonance. And the third one is showing transfer functions. And if we have a source instrumented, and then this should be different from the power spectrum, but if actually we don't have a source instrumented, so the downmost one is exactly the same as the middle data. I mean, the transfer function amplitude is exactly the same as power spectrum. Okay, so this is the measurements collected by the field test. And then now I'm going to show how those measurements were done at the real field, at the real concrete pavements. And the pavements is one of the rest area of the express highway. And then you see the trucks are moving around. It generates a lot of noise. And then I made measurements in the middle of the trucks passing by. Too close to show. All right. Ready? Yep. That's it. I like to show around the measurement device. As you see, this is the microphones, and microphones are replacing accelerometers. As you see at the bottom, this is small microphones. It is picking up the vibrations of the air pressure, more exactly the time histories of air pressures. So that is recorded by microphones. If we take two time histories of the microphones, and then those are equivalent to the accelerometer time histories too, right? Anyway, so here are the microphones replacing the accelerometers. The steel ball hammer is generating impact source, and it's generating surface waves propagating through the pavement surface. And as you see down here, this is a data acquisition system for recording the microphone signals and passing the signal to the computer screen. Let me change that screen to the surface wave. You see, this is time histories collected by two microphones, and this one is phase spectral difference from those two time histories. And as you see, it is clearly showing the sawtooth pattern pretty much. Okay, once the SSW test is done, and then we can go to the body wave resonance test, and this is also collected by the same device equipment. And this is the power spectrum of the first receiver, and we can see clearly the resonant frequencies. And utilizing these two measurements, so for saying surface wave measurements and body wave resonance measurements, and utilizing these two measurements, we can evaluate the thickness of pavement and also average sense of shear velocities of concrete material. Now the next one is to analyze the measured data. And once we have a good data collected, or you are satisfied with the data quality, and then go to the tab number 2, which is phase velocities. And also there are two different tabs, IR filtering, and the second one is phase velocities. Let's go to IR filtering first. And as you see, there are three different colors. The original is blue color, and enhanced data, which is going to be used for analyzing the data. It's kind of clearing up the noises a little bit, so it's showing improved, as you see. Just a moment. Yeah, this is improved. So it is coming from IR filtering. And then the last one is backbone, and then backbone is kind of backbone analysis, which is interpreting the data appropriately. The last one is backbone options. So backbone options, as you see, is going through the raw data, which is kind of nice trend. And then this is kind of an essential tool to look at or to understand the measurements more professionally, more realistically, or without being biased. So the last one is backbone curve, not biased by the environment noises or multiple reflections or something. So it is loyal to the main energy transportation. I'm sorry, the main energy propagations. The last one is backbone curve. And as you see, the backbone curve is going through the original data, which is helping us to understand, to avoid being biased by the environment noise or multiple reflections. Okay, and the next step is click on calculate the Gabor spectrum. Gabor spectrum is, let's go back to it, automatically moves to the tab called phase velocities. Now we are at the tab of IR filtering. So you are looking at the Gabor spectrum, which is kind of 2D contour map of time and frequency domain. And the brightest one, which is yellowish color, is showing the section of highest energy. And so this one is the one that we are going to rely on, that is wave group. So that wave group is the one we are going to rely on. If you go to this one, and that one is not the right surface wave wave group, and then we would like to pick up the most right one. And so if you see the selected, automatically selected region, which is the rectangular section with the green dots, if that is not corresponding to the surface wave group, and then you have to change it by clicking like this. You have to change it to the reasonable part of the wave groups. Okay. And then once you are satisfied it, and then you can click update and recalculate. But actually the one given by the software is reasonable. We would like to keep it, so I don't want to click on it again. And the result is shown right here. And so there are all different FK relationships, and then out of these many curve, grayish colors, the green one are selected. The green one is selected, which is the right understanding or right interpretation, and corresponding to these blue colors from, let's say, the frequency is 9200 to 44800 hertz. All right, so we are happy with this blue interpretation, and also you may want to take a look at the velocities also. It is ranging, let's say here, 2285 meter per second and 1800 meter per second. Those are reasonable values also. And so once you are satisfied with it, and then you want to go to experimental dispersion curves. All right, so in these plots, and grayish colors are original dispersion curve, phase velocity plots coming from this. And actually this is frequency domain if you are changing it back to the wavelength domain. But unfortunately this is linear scale. Actually that one is corresponding to this. This is logarithmic scale. So those are identical ones. And then out of these, the original plots, and then we picked up kind of representative data points with the blue dots. And maybe and the blue dots is 20 points, and compared with the original data of maybe 400 dots and 400 points. So we like to reduce the number of data points for interpreting, for performing inversion analysis more effectively. All right, so once we have this, the next one you want to do is check the data here, the data shown in the tables, and number of layers we are going to use for the analysis is 3. And then the topmost one is a soft, the relatively soft layer after a kind of poor curing, and the middle layer is the main sections, 25 centimeter. And don't worry about the velocities. This one is going to be updated later by inversion analysis, but densities and Poisson's ratio are not changed. We are going to basically using these values. But if you are not satisfied these values, you may want to change, but these are pretty much recommended ones. You don't want to change it. Okay, and 24 centimeter, which is a assumed after, approximately evaluated or estimated by looking at here, the wavelengths data evaluated by the surface wave test. And so it is showing the green dot, the blue dots is showing 23.8 centimeter. So this is going to be 0.24. And this is kind of first approximation. And secondly, so this is what you want to do now in this step. And we would like to have a starting model parameters before we perform inversion analysis. And so we need to have it by clicking run it. And then it is giving you the approximations. And then those approximation is updated in this table too. And the thickness is 3.3 centimeter, and the second one is 20 centimeter. And shear velocities is almost 1996, almost 2000 meter per second for the first one. And second layer is 2159 meter per second. And then as you see, the others are not changed. Interestingly, 200 meter per second is fixed, and that is corresponding to the shear velocity of subgrade. All right, so we are ready for performing the real inversion analysis. Now click on run. It takes a little bit, but it doesn't take that long. Okay, so the inversion analysis is done pretty well. And as you see, the red dots, open circles, are very nicely matched with the blue dots. And blue ones are measured by experimental field test, and red dots, red circles are theoretically determined. So that means the assumed or evaluated layering system, the thickness and the shear velocities are pretty good in terms of phase velocity calculations by looking at the comparison with two different data, two different velocities. So we are happy with it. And then after this, we are able to see estimated thickness. So this one is, it says 20 centimeter. I believe this is pretty good and practically too. So we don't have to perform resonance search. The analysis, maybe you can feel it later on, but we would like to see it, try it out also. All right, again, after, this is everything from in the aspect of SOSW measurements, SOSW test. So we have a 3-layer system, and thickness of each layer and the shear velocity each layer are determined, and then the thickness of the pavement system, 20 centimeter, is determined, evaluated. Okay, right. So we'd like to refine the thickness of these pavement systems by running enhanced resonance search, ERS technique. And in this ERS technique, what do we want to do? The thickness of the first layer is fixed. And then we are going to change the thickness of the second layer. And right now it's 24 centimeter, but we are going to change it from in certain ranges. So, okay, this is what we want to do. And the range of thickness is 20 centimeter to 21 centimeter. This is, determined using the estimated thickness from the SOSW test. And then our final goal is the resonant frequencies. And this one is true value measured by field test, ERS. Let me go to the right here. So by the body wave resonance, we measure the peak, which is resonance. The frequency is 8187. So that 8187 hertz is right here, and this is our goal. By changing the thickness, and then we want to find out which thickness gives us the resonant frequency of 8187. If some thickness is giving exactly this frequency, resonant frequency, we may say that thickness is the answer. Okay, so now let's run it. All right, so this is the first try, and then now we are going to second try. Trial thickness is 22 centimeter, and then it is performing fine sweeping, and then resulting resonant frequency for that thickness is this. So it's about almost 9,000. So 9,000 is higher than 8187. Now the third try is 25 centimeter thickness. Yeah, right here it's going to be about 6,500 hertz. The resonant frequency is getting smaller with increasing thickness. Okay, so right here we have run with 4 different thicknesses, and each thickness gives different resonant frequencies, and those relationships are plotted in the lower graphs, the log plots. And then as you see, so 0.3, 30 centimeter up down to 20 centimeter, whatever. And then we are looking for the slab thickness corresponding to the resonant frequencies. And resonant frequency 81, 87 is approximately here. And then thickness is about 20 centimeter, right? And then so the 20 centimeter is the gray line. And so this is enhanced resonance search technique. So by performing this series of physical modeling or analytical modeling, we can elaborate in determining the pavement thickness by looking for the measured resonant frequencies. All right, so, and in this case, interestingly, the estimated thickness from SOSW test is coincident with the thickness evaluated by resonance search technique. I may say, I don't have that many experience, but I may say these two different testing techniques are agree in most of the cases. So if you don't have time, maybe the SOSW thickness is good enough, but I strongly suggest you to utilize ERS technique that is more reliable based on others' experience. All right, so that's all in terms of the piScanner analysis. All right, and if you have any questions, you can reach me through the email address or phone numbers or KakaoTalk address, and I'm happy to answer all of your questions. Thank you so much for being with me in explaining all the details of piScanner analysis and technique. Thank you so much.